Star formation. Identical star formation speeds are as high as 1,000 solar masses per year. When we recognize such aspects, we likely see the final stages of ellipticals in formation. Indeed, heavy winds are virtually ubiquitous in ultraluminous galaxies. The flow rate is usually relative to the star production rate, hinting that the volume of ejected baryons is like that residing in stars. What is less apparent is whether the high performance needed for massive spheroid formation previously in place by a redshift of 2 is enough to the position of active galaxies in triggering star arrangement. Star development timescales as short as 10 million years are gathered from large elliptical galaxies. Star development timescales are defined by synthesizing the diverse types of stars required to consider for the detailed spectrum of the galaxy. We can understand from the colors and impact if the galaxy is young or old. One hint to the configuration is that current galactic cores are present and a meaningful section of the total amount of ultraluminous galaxies. Regrettably, there is a chicken and egg type of dilemma here. The overlap does not tell us whether the existing nuclei are a trigger or a result of the ultra-high rates of star development. Either way, something is required to expedite star formation, and supermassive black holes are a feasible element. Active nuclei believably play a double role in the spheroid form, both in triggering and increasing, as well as in quenching star configuration. A strong argument can be given that feedback, the transfer of stock between different revealing objects, performs an essential role in galaxy development. Unluckily, we do not have sufficient comprehensive information to reproduce in computer models the exact feedback mechanisms are at play when galaxies form. Our measurements, however, show us 3 sorts of activity on the mergers of galaxies, the dynamics of supermassive black holes, and supernova disorder. When the merger of 2 or higher galaxies takes site, it pushes gas into the center of the other massive galaxy. Thus, one finds evidence for merging and many ultraluminous galaxies. Gas-rich mergers plausibly drive the spheroid star configuration mode. However, there are not enough critical mergers, especially at high redshift, to consider all ultraluminous galaxies. Also, gas-rich mergers form ellipticals with distinct morphological properties suggestive of embedded disks because the gas obtains angular momentum, some of which is maintained by the recently formed stars. We solely do not see this outcome in the various extensive ellipticals. They could not have developed this way. Minor mergers are apparent in the classic gas supply method. The gas supply also feeds the middle supermassive black hole. Supernovae cannot estimate outflows from massive galaxies. The thermonuclear outflows play an indispensable role in quenching star establishment. Otherwise, various ellipticals are too bright and too blue. Active nucleus-driven currents are a natural result. Supermassive black hole extension is in condition with galaxy formation, or at least with the global star production rate. Our second case of feedback originates from supermassive black holes. They are served through the gas-rich state of galaxy configuration. The relationship of supermassive black hole mass with the spheroid potential implies that the development of both is contemporaneous. The starburst association with spheroid formation happens during the supermassive black hole growth period. Active galactic outflows can also trigger star formation before extinguishing it. The marvels are most probable causally related, but we do not grasp the associated arrow of time. Does supermassive black hole extension recede and trigger the spheroid formation of a supermassive black hole growth an outcome and ultimate terminator of spheroid formation? In the gas-rich development phase, the energy input from active galactic nuclei is prevailing by direction of magnitude, or more related to information from supernovae. Indeed, supernovae provide adverse feedback and galactic disks. They push from possible origins of low-mass galaxies. Supermassive black holes create outflows that present actual feedback and large demonstrations. Spheroids blowout transpires accordingly, and star configuration terminates when a supermassive black hole approaches a critical mass that depends entirely on the spheroid mass. The supermassive black hole quenching theory channels to a supermassive black hole spheroid speed dispersal correlation that implements the observed relationship among the black hole and spheroid mass in both incomplete condition and grade. Finally, the great explosions of supernovae and other active galaxy outflows play crucial roles and how feedback points to galaxy configuration in disk galaxies. Supernova remains self-regulate the interstellar medium, encouraging fountains out of the disk. The gas chills in the halo and eventually accretes on the disk as high-velocity clouds through spheroid configuration. The center supermassive black hole growth period results in discharges that induce stimulated star configuration. The induced supernovae can force winds even at the beginning stages of spheroid generation. Only when the supermassive black hole achieves its final mass is the existing galaxy wind powerful enough to wipe out the spheroid and eliminate all following starform. As noted, we do not have a vital mechanism in computer simulations to explain feedback. The situation is particularly grave and not possessing data to explain the forming of the spheroid overall. Here, one needs the overall disk gravitational uncertainty that sets the exhibition for star establishment in disk galaxies, for instance. This restlessness drives spiral density waves that, in turn, create molecular cloud networks. The next steps include cloud fragmentation and commotion generation. This process climaxes when the cloud nucleation fails and stars are created. Our knowledge of these progressive steps includes as much phenomenology, particularly our observations, as theory. Indeed, our modeling results depend solely on the phenomenological data. For instance, while supersonic disturbance is perceived to manage on all scales of the interstellar medium, what motivates the confusion is discussed between large-scale gravitational fluctuations, magnetically induced fluctuations, supernova bursts, and protostellar currents, which are all supposed to play a part. Most convincing, of all these climactic events in space, present information adds some level to disturbance over a wide assortment of scales. The product should be indifferent to the features of the input. If not, our patterns would be complex. Maybe the most critical issue is that whatever mix of physics is related to the feedback issues that we observe in the nearby cosmos, there is little incentive to ensure that a similar prescription continues at early interventions in the cosmos. Thus, all forecasts for the raised redshift cosmos, that is the initial cosmos, should be viewed as, at best, guided guesswork. Is dark energy meriting as the main aim in cosmology? This issue, in turn, is driven by a different one. Will we always possess a basis of dark energy on a different functional level? Given that we occupy a galaxy, will there ever exist a significant theory of structure development? While one can forever find inflationary patterns to explain whatever sensation is interpreted by the flavor of the month, the general forecasts associated with most of the inflation models have had two enormous successes. Nowadays, cosmology seems somewhat unexciting. All judgments converge on the conventional cosmological standard with its hypothesized components of dark matter and dark energy inadequately recognized. Future investigations focus on reducing the prevailing error bars, with the opportunity always lurking to find new signs of physics. Confidence that we have got the final answer requires enormous hubris, given our woefully incomplete mastery of the first example of the Big Bang. The terminal hypothesis of cosmology will undoubtedly carry our official cosmological model as a component. Time travel. Could we ever justify any of these theories? Does the multiverse hypothesis assert that many worlds exist? Only by judgment can we hope to question their presence. We require to go beyond. Our best play is to assemble a time machine to progress into another cosmos. This is far out of sense in terms of everything we are currently proficient in doing. Time travel between cosmos is a genuinely exclusive goal. To get beyond this, we first would require comprehending time travel within our perceptible cosmos. Let us state first, no basic law of physics prevents time travel. Success is unquestionably a topic of technology. Regrettably, we are far from the idea, let alone creating a prototype time machine. Nevertheless, let us apply our imagination stimulated by the theory of gravity. Time travel is likely in principle via wormhole technology. A wormhole subsists according to Einstein's theory of general relativity. It is a tie into different parts of space and time which can reach another cosmos. Of course, we have never identified a wormhole, but this must not prevent our considerations. After all, most of the cosmos is unexplored. Time travel is the unique way to examine the multiverse theory. We require to go there. This may be, and probably is, the realm of science fiction, but the rules of physics do not eliminate it. Moving far in space constrains travel and time. Space-time constitutes the fabric of the cosmos. We cannot divide the two, time and travel, that can be defined in the setting of physics. It is a fundamental precursor to moving across the universe. However, a journey in time involves clear inconsistencies that we demand to defy. It would not be a great idea to travel back in the past and eliminate one's great-grandmother for any alleged sin. There is an inconsistency since we cannot alter the present. One answer is that invoking quantum ambiguity permits us to bypass this paradox. One can confirm this by thought exercises on the quantum scale. Let us assume we can burrow into space by creating a tunnel like a train tunnel boring into a mountain. The substance of a space-time tunnel would require to be especially strong to stop it from falling under the influence of the neighboring space with its material and energy fields. Nevertheless, such a substance is no different in energy from what would be needed for a spaceship to start within the border of a black hole, a course that may be needed to find the most related wormhole. Shooting particles into such a hole through spacetime would occur in their appearance at an intrinsically unknown location in spacetime. The chances of meeting themselves on the way back would be imperceptibly small, so they could not be beaten off course on the way into the tunnel. Whether there is visible communication is not grasped, but seems reasonable. One would never more find one's great-grandmother. She would be covered in a cloud of quantum indecision. We all deprecate past mistakes. What would we not give to have another opportunity to return to that little contact with a person who never seen reason, or to retake that important examination? Or, for those annoyed by recent tourism opportunities, why not a detailed safari for Tyrannosaurus Rex, or a walking trip of the original 7 Wonders of the World? Physics states that all of this and more is plausible. Not today, neither tomorrow, but such events lie within the bounds of physics. Here is the procedure for the tunnel. Create a wormhole. This bizarre object prophesied to survive in Einstein's theory of gravity is a tunnel through space and time. It is only obtained through a black hole, so no answer is possible without breaking the laws of physics. Nothing can leave from a black hole. Quantum gravity, the latest hypothesis that unites gravity and quantum theory and is the holy grail of particle physics, claims that small black holes and wormholes live throughout space. However, their continuation is short, and they pass before we can take or even detect one. The void is thought to be leaking with such brief-lived abnormalities. Wormholes are there to be found, if only we understood how. The trapping, though, can be done without breaking laws. It simply requires acquiring a very stiff substance that opposes gravity. Virtual wormholes should subsist. For temporary instances, according to quantum gravity theory, catching one would require unimaginably powerful forces. Entering one may be severe. It could cause against itself. Our safest bet may be to find a vast spinning giant black hole. Many numbers of massive black holes are known, often sneaking at the centers of galaxies. As one contemporary astrophysical theory, even our Milky Way actively suggests that all black holes revolve because most huge stars are spinning quickly. These stars are the ones doomed to form black holes. A few will arise to reach beastly dimensions. The one at the heart of our galaxy measures 4 million solar masses. Only if the closing stages involve rapidly spinning matter can one understand how to find a wormhole. A quickly rotating black hole has a twisted event horizon. Typically, the event horizon stops the random observer from reaching the central singularity. An event horizon is impassable for the external observer. Time crumbles to a standstill. Nevertheless, with rotation, the singularity becomes easy. It can likewise be visible with no protecting event horizon. One can reach one of those and attain the primary irregularity where a wormhole might be for the amateur explorer. The technology for a spaceship to survive entrance into the event horizon of a black hole needs material of incredible durability. As one progresses the event horizon, the tidal strengths become immensely strong. Any recognized element would be torn to shreds, but adequately stiff material should endure, at least in principle, to outlive the journey. Indeed, the matter in a neutron star has the necessary strength to withstand being stretched apart by gravity near a wormhole. Constructing a spaceship out of such an element borders on fantasy now, but science fiction has a practice of becoming a fact. Behold the writings of Jules Verne and H.G. Wells. Even stranger material that counters gravity is in deeply diluted form. We call this the dark energy that is accountable for the perceived acceleration of the cosmos. Time machine technology would ask us to control this force, use it to prop open a wormhole before it locks up, and stretch up the wormhole to a large enough hole for the courageous time traveler to leap in and fade from clarity. Of course, going back to the position where one initiated out would produce an additional difficulty to our fearless Voyager. Nevertheless, possibly they are only too willing to jump to new horizons, mainly if there is limited choice. At least one scientific obstacle must be surmounted. Firstly, the hypothesis implies that once a wormhole is initiated, it would quickly accrete material and fold in on itself, factoring in a difficult challenge to our ultimate wormhole engineers. A more solid strategy might be discovering a pre-existing wormhole in the center of a rapidly rotating black hole. Technical issues aside, this type of time travel is our safest bet for the investigation of spacetime. Regrettably, it is far afield from any technology we can directly perceive, filed by the American academic Michio Kaku as advanced technology of Type 2. Such technologies are obtainable in possibly 1 million years without breaking any of our cherished concepts. When we speculate about the future, the words of the old natural philosophers give some outlook. Roman philosopher Lucius Seneca died circa AD 65, for instance, and wrote in his Essential Questions Book 7, "The moment will come when careful research over long terms will lead to light matters that now lie hidden a single lifetime. Even those solely devoted to the sky would not be suitable for studying so vast a topic. Hence, this knowledge will be released only during long succeeding terms. There will reach a point when our descendants are amazed that we did not understand things that are so simple to them. Many revelations are maintained for ages yet to come when the thought of us has been obliterated. Our cosmos is a tiny little event unless it has in it something for each age to study. Nature does not share her secrets once and for all. Humanity has controlled high-level technology. As we now conceive of it, growth has been teetering for less than a century. We have joined the department of what the classical Greeks ascribed to the gods. We have mastered flying robots and space journeys, achieved virtually immediate video conference at vast distances, and managed discharges of virtually limitless power. Imagine what we might be able to perform in a century, in 1,000 years, or 1,000,000 years. It would be a foolish person who declared that our knowledge of physics prevented our capacity to master a time machine. On the other hand, of course, contemplate the subsequent cases. Heavier-than-air flying devices is absurd, stated Lord Kelvin, President of the Royal Society, 1895. If the quantum hypothesis is correct, it implies the passing of physics as a science, stated by Albert Einstein. Anyone who assumes a source of energy from the conversion of these atoms is speaking moonshine, stated physicist Lord Rutherford in 1935. There is not the sparsest evidence that nuclear energy will ever be achievable, stated Albert Einstein. To summarize, physicist Lev Landau states, cosmologists are frequently in error but never in disbelief. We have come a great way since Newton in terms of our knowledge of the physical world. What could we expect in forthcoming decades, or might we expect a new hypothesis of cosmology? Much of the perceived cosmos already suits into position the grand system of things. However, there is one factor in common with Newton's worldview that ought to provide us a basis for suspecting that we understand all the fundamental physics. Newton brilliantly anticipated, because of gravity, the creation of an almost eternal number of celestial bodies. The force of gravity unavoidably led to uncertainty, and planets and stars had to develop. Nevertheless, Newton could not know in terms of known physics why some things were luminous, like stars. Nevertheless, others, like planets, were not. Newton advanced to a greater authority to resolve his predicament. The physics finding only emerged 250 years later, when Hans Peter understood what it took to produce stars that shine, particularly thermonuclear power. The discovery of dark matter models one of the most critical problems. It is universally confirmed by several sovereign types of investigations, but we have not distinguished a single candidate particle. This situation has driven some astronomers to challenge the very justification of gravity. Possibly the gravity law demands to be altered. Then we can dispense with dark matter solely. Nor is dark energy in any more reliable state. Suppose we remove the data from supernovae for the quickening of the cosmos. After all, we require a technical model of supernovae. No one could object that using a measuring tool whose ideological foundation is unknown is a high-risk system. There could be evolutionary systematics that simulates the dimming of the most remote supernovae. Maybe intergalactic dust does the dimming. Then we would not require acceleration. We know that something controls the mass-energy density. 2/3 of it is not gravitating material. That changes the large-scale arrangement of the galaxies. It could be something entirely uniform, for example, a new power field. Nevertheless, this appears an even more thorough explanation than Einstein's cosmological constant, which provides all popular data. The situation is curiously suggestive of our conversations about the multiverse and the anthropic origin. Perhaps we require the correct physics hypothesis to cope with the severe restrictions at the origin of the cosmos. There are solely too many issues that occur in our present classification of the cosmos. Buried within these mysteries could well be the roots that give rise to a prospective theory. Fortunately, we are not in a rush. Billions of years of research lie onward, provided, of course, that humanity does not self-destruct. The Sun will exist for another 5 billion years. It has almost entered middle age by stellar models. There is much we cannot conceive of yet which may be available on such a timescale. We are on the brink of discovering hordes of Earth-like planets. Many of those will be more mature than the Earth. With a billion years head start over Homo sapiens and our culture, one cannot start to guess what culture in some distant galaxy anonymous to us might be proficient in manufacturing. Of course, this does imply that the development of life is not improbable. Given the right conditions, we will never be sure of the result until data is found. Our investigation of the cosmos need not inevitably be defined in space and time. We may find a nearby wormhole or plane singularity and utilize it as a time machine. We may improve the technology to be capable of traveling to another cosmos. We will see how the cosmos began. Furthermore, no uncertainty exists that we will begin to conjecture the nature of dark energy and dark matter.
Jai Mamari Nina. Tuda la ba. Kopana, Dana, Tula. Papa na, Lana, Gemma Marina.